Well, the title of this lecture is Experiments, and while everybody has their idea of an experiment maybe as being a guy in a lab coat working with test tubes, in this sense an experiment the word experiment is used in its more general abstract meaning of creating a controlled setting. And so I'm going to start out with examples that we'll be thinking about for our experiments. And one of these, a very simple one, tossing a coin. You take a coin and you toss it, and you note whether it's a head or a tail. So one example of an outcome for such an experiment would be, hey, it's turned up heads. And so the sample space, the set of all things that could happen, would be, oh, it could turn up head or it could turn up tail. So we have an idea here of what can happen. We've taken our experiment and we've thought it out before we've started. And we say this is what can happen, and we can do our design in the light of that. If it falls off the table, well, that's not part of the sample space. Okay, if it lands on its head, okay, this is not part of its sample space. We would not accept those as outcomes from our experiment, and we would scrap it if it doesn't come within this sample space. Throwing dice. Okay, you can throw a pair of dice and you have one of them come up 5 dots and say the other one come up 2 dots. That's an example of something that could happen. And here we have a listing of all the possible things that would happen. There are 36 different things that can happen when you throw dice, and here we consider the dice to be separate entities. Think of one as being green and one as being blue, and so that you'd be able to keep them separate. And so there are 36 things we could have. The first die could be 1, and the second die 1, and the first die 1, and the second die 2, and so forth, until you exhaust all possible ways that this could come up. And there are 36 different ways. Another experiment, probably something you haven't thought of, checking your watch. Okay, you check your watch and you read a time, 12:13. Most of our watches, even if it keeps seconds, we don't note it out to the second, we just note it to the minute. And so 12:13, and this would be what could happen. One thing that could happen, we would have a listing of all the possible outcomes, and this sample space is created with the assumption that you have an American style watch that only goes up to 12, and not a European style watch where you go up to 13. I was setting my watch and accidentally switched it over to 24-hour mode. It drove me out of my mind until I accidentally switched it back. Another example of an experiment, you have a survey question and ask, okay, do you drink coffee? What are the possible outcomes of this? Well, one outcome would be yes, I do drink coffee. We frame the experiment here that's either yes or no. If you're giving a questionnaire and somebody writes down sometimes, you need to decide how you score that. Okay, if these are going to be the only answers that you accept, because this is all about thinking ahead and having a plan on how you deal with the outcomes of your experiment. Another one, flip a coin until you get a head. Okay, so the idea, you flip, if it comes up heads, you stop, experiment's over. If it comes up tails, you take it and you flip it again, and each time noting what happens. So here I said you flipped and got tails, you flipped and got tails, and then you flipped and got a head, and then you stopped. And here we have a listing of all the possible outcomes, and as you can see, it's just going to be a longer and longer string of T's, but each time it will be terminated by an H, because that's what the experiment is. You stop when you get ahead. Okay. There are different ways of characterizing sample spaces. We characterize them first in terms of their number. They're either finite or infinite. The second is a bit more subtle. We characterize them in terms of their topology. And this we're not going to make as big a deal of, because it's kind of a more advanced concept. Again, we will deal with it in terms of examples. Okay, finite sample space means that you can count their outcomes and stop eventually. So head, tail, you can assign, there are two outcomes in this. Okay, yes, no, there are two outcomes in this. This one with the dice, you can assign a number to it. There are 36 outcomes. So these are finite sample spaces in that you can assign a number to their size. Okay, infinite sample spaces, infinite means you cannot assign a number to their size, and so this one you can count 1, 2, 3, 4, 5, but you never stop. Okay, you can't assign a number to this size. It's infinite. Okay, here, measuring the temperature of a liquid with arbitrary accuracy. Well, here there are an infinity of possible outcomes, and here again it gets technical because so much of it depends upon, you know, how fine you do your measurement. Okay. Anyway, this is a point where, in fact, what I call the topology of the space comes in and makes it more complicated. So this brings us to the discrete versus the continuous. Discrete random variables are those whose values can be isolated from each other in disjoint intervals. Okay, there are discrete random variables that are finite. In fact, if it's finite, it's going to be discrete. There are also infinite random variables that are discrete, but those are the ones where you can isolate their values. Continuous random variables are ones which assume complete intervals of values, and again, even here I'm being a little bit imprecise. Okay. One type of experiment which we will be coming back again and again is called a Bernoulli Trial. Okay, Bernoulli Trial. It's an experiment with two outcomes. We label them as success or failure. Okay, you can succeed or you can fail. There are only two ways to do it, and we let P denote the probability of success. And the classic example of the Bernoulli trial is I symbolize by having a can. This used to have an animation with it that worked, and I would have a red bead popping out of this one and a blue bead popping out of this. So the idea is you have a can with two kinds of beads in it, red and blue. Right? You reach in and you pick one and you take it out, and you've decided that, okay, red is successful. So you pull out a bead, you say, it's red, that's success, you put it back in. Now if you pull out a blue, you say, okay, that's failure, you put it back in. And so the idea here is that say you have a situation where you have 1,000 beads and 750 of them are red, then that would give you a probability of success of 75. And so you conduct an experiment, okay, with this. You pull a red one, pull a red one, pull a red one, and each time you're putting it back afterwards so that you don't change the probability. I conducted this experiment, had Excel, pull 30 random numbers, and conducted this experiment, and when I did it, I had success 21 times, failure 9 times. Notice, okay, it doesn't hit it dead on, okay, but we do get more successes substantially than failures, because it is quite a bit bigger a probability of success than failure. And so think about it. If the probability of success is 0.75, what is the probability of failure? This is an example of a complementary event, and so the probability of failure is 1 minus 1.75, which turns out to be 0.25, right? And so again, Bernoulli trial has 2 outcomes, success or failure, and we have a probability P of success. And so that ends this.